Why Japan's railgun changes, everything map showing Japan, China, North Korea, Russia. China, North Korea, Russia, 3 countries, 3 different kinds of friction. But for Japan, they all hit the same nerve, a direct challenge to vital national interests. These tensions don't stay at the negotiating table. They show up in disputed waters, in missile flight paths, in territorial disputes that never truly closed after World War II. So, what does a country do when it feels boxed in? It strengthens defenses, it leans on allies, and it tries to keep tensions from spiraling out of control. But geopolitics doesn't always reward restraint. Sometimes the safest move is to make the other side calculate the cost of acting. Visual, JS Asuka at Yokosuka Naval Base. Summer 2025. Tokyo chooses that route. Railgun mounted on JS Asuka deck, Yokosuka. On the deck of the test ship JS Asuka, an unfamiliar weapon system appears. Not in a laboratory, not on a concept sketch. On a real ship, at a real naval base. Headlines move fast, and the labels get loud. An electromagnetic death ray. A weapon that can pierce armor and stop hypersonic missiles. Something that used to exist only in science fiction. The weapon is an electromagnetic railgun. But the label isn't the story. What matters is what sits behind it. Is Japan's railgun really as powerful as the rumors suggest? And if this is the technological path forward, why did the United States, once far ahead, pause its own program? Cross-section animation of conventional gun. Before we talk about what railguns might do in combat, one basic point comes first. How is it different from a conventional gun? For centuries, artillery has relied on the same core principle: explosives. Propellant burns inside the chamber, creates superheated gas at extreme pressure, and that pressure drives the projectile out of the barrel. Visual, animation showing limits of conventional guns. By the 20th century, humanity pushed that principle hard. Want more range? Lengthen the barrel? Want more power? Add more propellant. But eventually, every approach hits the same ceiling. Pressure can't rise forever. A barrel can't endure unlimited heat and force. Put simply, conventional artillery runs into the physical limits of its own design. Railgun schematic animation. Railguns appear at that dead end and take a different route. A railgun doesn't use explosives. Inside an electromagnetic railgun, 2 parallel conductive rails carry an enormous electric current. That current generates a powerful magnetic field, and the interaction between current and field produces the force that hurls the projectile forward with brutal acceleration. Comparison graphic. Think of it this way. If conventional artillery is like an internal combustion engine burning fuel to create thrust, a railgun is more like an electric launcher. It dumps energy straight into the projectile in a very short moment. That brings clear advantages: higher velocity, longer range potential, and the projectile can be non-explosive, relying purely on kinetic energy. At that speed, even a non-explosive projectile hits with enormous kinetic impact. And higher speed compresses the defense timeline, leaving less time to detect, track, and react. But one point has to be stated plainly. A railgun is not magic. It doesn't automatically replace conventional guns. It's simply a different evolutionary path that changes the underlying principle to move past old limits and inherits a new set of constraints in exchange. First photos of railgun on JS Asuka. Japan is one of the very few countries willing to push far enough to turn this from an idea into a working system. According to the War Zone, the first images of an electromagnetic railgun mounted on the helicopter deck of JS Asuka appeared in April 2025. Those images did more than confirm the system exists. They revealed how Japan is trying to make it practical. Visual, close-up of support equipment. The gun appeared without a protective shroud, likely to give the crew easier access for maintenance. Around it sat large containers believed to house generators, capacitor banks, and support systems. And that detail matters. A railgun demands enormous electrical power for each shot. If the power supply stays too bulky, it limits where the weapon can ever go. That's why ATLA, Japan's Acquisition, Technology, and Logistics Agency, prioritized something that sounds almost backward: reducing the energy required per shot. Less energy means fewer and smaller support systems. And that's a prerequisite for mounting the weapon on a true warship later, where space is far tighter. Performance specs graphic. The implication is clear. Japan is no longer treating this like a lab demonstration. They're treating it like a shipboard weapon system that has to fit, operate, and be serviced at sea. On performance, ATLA has stated its experimental railgun can fire projectiles at speeds up to Mach 6.5 with roughly 5 megajoules of energy per shot. These aren't theoretical figures. They're parameters demonstrated through testing. ATLA's next target is 20 megajoules. That's the step aimed at sharply increasing range and lethality. Barrel wear diagram. But the hardest challenge runs alongside every performance goal: barrel and rail durability. Each shot subjects the system to extreme conditions, accelerations on the order of tens of thousands of Gs, severe heat, massive electrical currents. ATLA is working to push barrel life to around 120 shots before replacement. That may sound low, but in railgun terms, it represents meaningful improvement, and durability isn't a side issue. A weapon that can't sustain fire without frequent maintenance is a weapon that can't be trusted in a high-tempo fight. JS Asuka firing at sea. On September 10, 2025, ATLA confirmed this. During June and July, the Japan Maritime Self-Defense Force conducted live firing at sea from JS Asuka, including long-range shots and successful hits against a surface target. And the location matters. Firing at sea is always harder than firing on land. From that point on, Japan's railgun was no longer just a future concept. It became a system tested in conditions closer to real operational use. U.S. Navy railgun testing footage. But the most revealing detail isn't Mach numbers or megajoules. It's how Tokyo talks about the project. Japan isn't claiming the railgun will replace naval guns. They're not branding it as a game changer. They frame it as a platform undergoing serious methodical testing. And that cautious framing leads directly to the next question. If Japan is moving forward step by step, why did the United States, once far ahead, choose to stop? Timeline of U.S. railgun development. There's a common misconception that Japan is the pioneer and the United States is only watching. The reality is the opposite. The United States was the leader in railgun development, and for years it was far ahead. In 2005, the Office of Naval Research formally launched a naval railgun program. By 2008, the first railgun was test-fired. At its peak, this wasn't a symbolic project. U.S. test specs. Early tests fired a 7-pound projectile with muzzle velocities up to Mach 7.4. Later phases pushed harder. A 33-foot barrel, projectiles up to 44 pounds, pulse power reaching 32 megajoules, theoretical range beyond 200 nautical miles, and a projected firing rate of 6 to 12 rounds per minute. On paper, the economics look compelling. Internal U.S. Navy estimates suggested generating 1 megajoule of muzzle energy, with conventional guns cost around $100. With a railgun, the estimate was roughly $1. Zumwalt destroyer. The peak ambition was integration onto a Zumwalt-class destroyer, a platform built around an advanced integrated power system designed with future weapons in mind. From the outside, everything looked aligned. Technology, budget, a suitable platform, and years of lead time over the rest of the world, which is exactly why the decision to halt the railgun program felt like a shock. Visual, technical challenges graphic. Why stop? Not because they couldn't build it, but because they reached a cold conclusion. Being able to build something doesn't mean it should be fielded. The first obstacle was durability. In U.S. testing, practical rail life amounted to only a few dozen shots before major maintenance. For a Navy that deploys ships for long stretches far from home ports, that becomes a mission-level risk. The second obstacle was the projectile and guidance problem. To realize full potential, the projectile must hit targets at extreme range. That implies a smart round with sensors and control systems. But a railgun launch is brutal. Accelerations of tens of thousands of Gs. Intense electromagnetic effects. Guidance electronics have to survive the launch, and without that, extreme range becomes theoretical. not practical. Visual, power system diagram. The third and most serious barrier was power. Each shot can require millions of amperes, forcing a ship to generate, store, and release power with extreme precision. In practice, balancing propulsion, radar, electronic warfare, lasers, and a railgun on one electrical system proved extraordinarily complex. All of this led to a practical conclusion. The railgun didn't align with America's global expeditionary warfare model. Instead of redesigning fleets around it, the U.S. Navy shifted toward alternatives that integrated more easily, close-in defensive lasers and hypersonic missiles.